Hello everyone, welcome back to another physics video. I'm Physics Michael, and today we're going to explore stationary waves. We will learn what stationary waves are, how they form, and the special properties of stationary waves. Let's get started. Let's begin by comparing progressive waves with stationary waves. You are already familiar with progressive waves. They have moving wave patterns that can transfer energy from one place to another without moving matter. But stationary waves are different. As their names suggest, they have stable, long-moving wave patterns. And unlike progressive waves, they can't transfer energy from one place to another. Next, let's learn how we describe stationary waves. We can draw the wave pattern of a stationary wave using two extreme positions. Just as shown in the figure, the stationary waves on a spring show a series of loops separated by special points. These special points are called nodes and antinodes. Here, a node is a point on the wave that doesn't move at all. It has zero amplitude. We sometimes call these points minima. And an antinode, on the other hand, is a point that moves the most. It has maximum amplitude. We can call these points maxima. You can actually see these nodes and antinodes on a vibrating string, just as shown in the video. Now let's understand how stationary waves form. A stationary wave is produced when two progressive waves meet under specific conditions. They must have the same frequency and they need to travel in opposite directions. Look at the animation. We have a green wave moving to the right and a blue wave moving to the left. When these waves combine, they create a red resultant wave. Notice how the resultant wave's pattern stays in place. It vibrates up and down but doesn't travel along the string, hence a stationary wave is formed. Next, let's look at some important measurements and properties in stationary waves. First, the separation between two adjacent nodes is equal to half a wavelength. The same is true for the separation between two adjacent antinodes. It's also half a wavelength. Then, we can use the wave equation. Wave speed equals frequency times wavelength to calculate the speed of the progressive waves that form our stationary wave. And the phase difference between points on a stationary wave depends on the loops. As you can see in the animation, all points within the same loop are moving in step with each other, or we can say they are vibrating in phase with each other. But if we look at the 2 points in adjacent loops, they are vibrating in antiphase. Let's solve a practical example. Imagine we have a string fixed between 2 points, x and y. That's 78.0 centimeters long. A stationary wave forms on the string, creating 4 loops, and the string vibrates at a frequency of 120 Hz. What's the speed of the progressive wave on the string? Let's solve this step by step. With 4 loops, the distance x to y equals 2 wavelengths. So one wavelength is 39.0 centimeters, or 0.390 meters. Using the wave equation, speed equals frequency times wavelength. 120 times 0.390 equals 46.8 meters per second. Let's summarize what we've learned today. Stationary waves are formed when two progressive waves with the same frequency meet while traveling in opposite directions. They have stable, long-moving wave patterns with nodes and antinodes. The distance between adjacent nodes or between adjacent antinodes is always half a wavelength. And remember, points in the same loop vibrate in phase, while points in adjacent loops vibrate in antiphase. That's all for today's video. Thanks for watching. I hope you now have a better understanding of stationary waves and how they work. I'm Physics Michael, and I will see you in the next video.